that's the plan. Okay. Great. So taking off from last time, remember we were talking about polynomial time reductions from one problem to the other, and the reason we wanted to get a hand on reductions is because we would want to study the relative hardness of problems. Yeah. So we know that a few problems, in fact, several problems which arise in practice, they seem to be very hard to solve. We don't know good efficient algorithms to solve them. So the question is are these problems somehow related to each other? Okay. So again, in this lecture, I'm just going to show you the tip of the iceberg. I'm not going to be very formal. This is really a topic of an entire course in computer science. And perhaps you are going to see, so those of you who are already taking theory of computing will probably see a part of these things in somewhat more formalism in that course. But today we would just kind of, it's almost a very, very informal treatment of the whole business. Okay. Okay, so remember we were trying to do a reduction last time from the 3-SAT problem to the independent set problem. Okay, so let's just quickly recap the definition. So what was 3-SAT? So I'm given a Boolean formula, and each so the formula looks like this, right? So it's a conjunction of several clauses, and each clause will have a disjunction of some literals. Okay, so literals are Boolean variables or their negations. So either it will have an xi or it will have an xi bar. Okay, so those are literals, and yeah, you just take the odds of some literals and then you take the ands of these clauses. That gives you a satisfiability instance. And the question we ask is, so the decision problem is, does there exist an assignment for these xi's so that this formula is satisfiable? Okay, and 3-SAT is really a special case where each clause will have at most 3 literals. Okay, so I made a small mistake last time. I said that they will have exactly 3 literals. So for 3-SAT, this is not required. Okay, although for all practical purposes, okay, let me come to that. So yeah, 3-SAT means that each of the clauses will have at most 3 literals. And then there is another version of this, which is called the exact 3-SAT problem. Okay, so let me just call this E3-SAT. Okay, so this means that every clause will have exactly 3 literals. Yeah, and I'm just doing this so that it's easier for me to show you the reduction from E3-SAT to independent set. Okay, there is no other real reason to do this. Okay, so how do we do this reduction? And remember, what is the independent set problem? Well, it's simply we are given a graph, simple undirected graph, and we seek a subset of vertices such that this set does not have any edge between any pairs of vertices. Okay, that's the independent set problem. And again, the decision version would be, given a number k, does there exist an independent set which is of size k? Okay, right. So let's do this reduction from this E3-SAT to independent set. Okay. So suppose that we are given this instance of the 3-SAT. Okay, so that's your 3-SAT formula which is given to you, and you need to answer the question of whether there exists satisfying assignment or not. Okay, and the way we now reduce it to the independent set problem is the following. So of course, since it's independent set, we have to construct a graph. Now the graph looks as follows. So for each clause, I create a triangle. Yeah, so yeah, each of them has 3 vertices. I know because there's an E3-SAT instance. So I create a triangle for each of the clauses, and I label the vertices with the corresponding literal. Okay, so for example, in this picture, because I have let's say the first clause is x1 or x2 bar or x3, so I have labeled these vertices accordingly, right? Okay, similarly for the second one, I have x1 bar, x2 and x4. The third one again has x4 bar, x2 bar and x3 bar. So note that I think there was a slight confusion about this in the last lecture. so every time a particular literal appears in the formula, I'm going to make one copy of the corresponding vertex. Okay, so think of each of these x2 bars as independent copies of x2 bar that I'm making for reducing it to the highest instance. Okay. So that's the basic, and these things are often known as gadgets. So these are known as the gadgets of my reduction. Okay. So these are terms which you will hear often if you again take a course on complexity theory. So these are the gadgets which we join with each other and build a bigger instance of the problem. Okay. And now, so yeah, I said that I'm talking of the E3 set problem, right? So each clause has exactly 3 literals. So this is the E3 set problem, exact 3 set. Yeah. Okay. So now in addition, we will have some more edges in my graph. So how does the edges look like? Well, in some sense, these edges will denote conflicts among literals. Yeah. So the idea is that okay, and why are we introducing these new edges? Because the intended semantics of this reduction is the following: that if in my satisfying assignment I end up setting, let's say, x1 to be 1, then I know that x1 bar have to be 0, right? And when I translate this solution to the independent set solution, then I would pick the vertex from the first clause, let's say, corresponding to x1, but I don't want to pick the vertex which corresponds to x1 bar, right? Because I only want to pick the vertices for which the corresponding literal has been set to a 1. Okay, so the crux of the construction is that if I pick up the vertex x1, then I should not pick up the vertex x1 bar for the independent set solution. Okay, so how do we ensure that? Well, I ensure that by introducing an edge between vertices which have so-called conflicts. Yeah, so which is why there is an edge between x1 and x1 bar. There's an edge between x2 and x2 bar. So for each of these conflicts, we will introduce an edge. Okay, there is one more question. But then the other symbol triangle can be picked up as well. So why is there an edge between them? How can other symbols be picked? X1 and X2 complement. No, so okay. So let's do the reduction. Let's complete the proof. Then maybe this will answer your question. Okay. Yeah. Yeah. Just hold on till we end the proof. Okay. So let's see how we start with an instance of E3 set and form an independent set. Okay. Good. So now suppose there exists an yes instance to E3 set. Okay. Now here is the observation that okay. So again, it seems like today is a bad day because I'm writing something, but it's not showing up. Okay. Yeah. Let's see. Let's hope. Let's see how much we can do. Okay. So the point is, so suppose I'm given an yes instance for the E3 set problem. Okay. Now, what does this mean? This means that each of the clauses evaluates to a 1. Okay. Otherwise, there is no way that an E3 set instance is going to be satisfied. Now, if each of the clause evaluates to a 1, it means that there is at least one literal for each clause which has been set to 1. Okay, there might be more than one, but I don't care about that. I just want to say that there is at least one literal for each of these clauses which is set to 1. So I go over all the clauses and I collect exactly one literal from each of the clauses which has been set to 1. Okay, so for instance, I don't know what is a satisfying is there a satisfying assignment for this formula? I don't know. Maybe there is, but yeah, let's not go to that. Okay, so is this clear to everyone? So I know that I have an yes instance to E3 sat, which means that for each clause there is at least one literal which is set to 1. So I keep picking that one literal from every clause, and I pick the corresponding vertex in my independent set instance. Okay, so this implies there exists at least one literal for each clause set to 1. Okay, so pick the vertex corresponding to that literal. Okay, and now the observation is that this set forms an IS of size k. Okay, so yeah, the claim is that the set of vertices which you have picked in this process, this set, well, it has only size k because you are picking one, you are picking only one vertex for each of these clauses. So it has size exactly k, in fact. And why is this an independent set? Well, first of all, for each clause you are picking exactly one vertex. So you are picking exactly one vertex out of each triangle. So there is no conflict inside the triangle. And the only thing that remains to be shown is, can it happen that, you know, these kind of edges that go between two triangles, they cause a conflict. Okay, but clearly that cannot be true, because if some literal xi has been set to 1, then clearly x1 bar cannot have been set to 1, which means that if you pick xi, you could not have picked xi bar, you could not have picked any copy of xi bar in your independent set, right? So these kind of edges will not affect your solution, which means that this is an independent set. Okay, Oshin, does that answer your question? Okay, great. Good, but this is not yet done, right? So this is only one direction. This shows that if I have an yes instance to E3 sat, then I will have an yes instance for the independent set problem. Okay, now suppose, so let's prove the converse. So suppose there does not exist a satisfying assignment to E3 sat. So this will imply there does not exist an independent set of size at least k. Okay, so we have to prove both the things, otherwise this is not a complete reduction. So whenever you have to do a reduction, you have to make sure that both these are valid, because remember, the eventual goal is to use an algorithm to solve independent set to solve E3 sat. Yeah, so we are reducing E3 sat to IS. Okay, great. So why is this true? So the easiest way to do these things is to prove the contrapositive. Yeah, so I hope all of you know what that means. So we prove the contrapositive statement, which is that if there is a no instance for independent set, if there is an yes instance for independent set, then this will be also there will also be a satisfying assignment for E3 sat. Okay, so the contrapositive is yes instance for IS implies there exists a satisfying assignment. Okay. Now, why is this true? So suppose you are given an yes instance for the independent set problem on this kind of instance. Okay. Now, what does this mean? Well, yes instance means that there are at least k vertices there is an independent set which has at least k vertices. So first observe that the size of the independent set will be exactly k. Yeah, because it cannot be more than k. Why can't it be more than k? Okay, why can't it be more than k? Why can't it be more than k? No. Okay. So we are now taking the wrong route, right? Remember, we are not given anything about clauses so far. All I'm telling you is you have this graph and you have an independent set of size k. You don't know whether this graph has clauses or whatsoever. You just have this graph. The only information I gave you is there is an independent set which is of size at least k. And now I'm claiming that the independent set then would be of size exactly k. It cannot be larger than k. So what is the reason? So it has to do with the structure of the graph. It has nothing to do with whether there are clauses or not. I mean, this is a valid graph anyway. It doesn't. Right. So yeah, so the answer to this question is that suppose you have k plus 1 vertices in your set, but that means that there is at least one triangle for which you have picked at least two vertices, right? But then if you pick two vertices from a triangle, that cannot be an independent set, right? So if I'm given this information that the independent set is of size at least k, this means that it has to be size of exactly k. It cannot be more. Okay? Everyone with me? Moreover, I know that I could not have picked two vertices in the independent set which conflict with each other. Okay? Because, yeah, I mean, that's clearly not true. Then it won't be an independent set. Now, if these two information are given to us, then what we can do is exactly the opposite of what we did for the other side. So now look at your independent set, and now I know that, well, every triangle corresponds to a clause. You just make that corresponding literal to be 1. Okay. So what I mean precisely is the following. So suppose, I don't know if this is a correct answer. Suppose this is your independent set. Okay. So I don't know, maybe this is a wrong assignment. I'm not sure this is correct. Okay. So if this is an independent set, then all I do is I just turn these corresponding literals to be 1 in my Boolean formula. Yes. And then I know that it has to be a satisfying assignment. Okay. So that's the complete reduction. Okay. So how do I do this? So this implies IS is of size exactly k, since only one vertex can be picked from each triangle. Okay. Further, two conflicting vertices cannot be picked. Okay. This implies assigning the literals to 1 forms a satisfying assignment. Okay. Okay. Any questions about this reduction? Everything clear? Okay. So now that we are equipped with reduction, let's now go back to the question that we started with. So why did we introduce this idea of reduction? Remember, we are trying to study the relative hardness of problems. Yeah. So again, say you want to convince yourself that, so suppose pi is very hard. Okay, so pi is a problem and you want to convince yourself that pi is very hard to solve. Yeah. So one way, now that we have this formal notion of a reduction, so one way that I can try to do this is I can choose a very big set of problems. Yeah, so think of this as a very big set of problems, and I can try to show that all these problems have a polynomial time reduction to pi. Okay, so I can pick each and every problem. How I do that is not clear, or even this is possible, that's not clear. But one way to do this, to convince ourselves that pi is quite hard, is to show that you pick a bunch of problems that we already know to be hard. Know in the sense that we have tried them for quite a while, but we don't have an efficient algorithm. And you show that, well, there is a polynomial time reduction from each of these problems to pi. Okay. So let's start thinking. So what could be this set of problems? Okay, which are the problems that, so suppose pick your favorite problem that you want to show to be hard. Let's say TSP. So let's say pi is TSP. So I want to show that a very large set of problems can be polynomially reduced to TSP. Okay. So this is what I'm hoping for. I don't know whether that is possible. Okay. So one, kind of trivial way to start this exercise would be to assume to be extremely sort of optimistic or pessimistic, whichever way you want to look at it, and imagine that all the computational problems in the world are actually polynomially reducible to TSP. Okay, so let's say you start with this very large set to be the set of all computational problems. Okay, so we are being very ambitious. We are saying that maybe it's true that all computational problems boil down to solving TSP. If you can solve TSP or 3SAT or whatever your favorite problem is, then you will end up solving every computation. So what I mean by a computational problem, simply it means that which can be solved by writing a computer program. Okay, by writing a step-by-step algorithm in the sense that we have learned. That is the definition of computational problem, which I'm using here. Okay, so let's say that this is the ambition I have to prove. Okay, now, good. So I don't know if all of you have taken TOC or not, but those of you who have, do you think this is possible? So can I hope that all computational problems can be polynomially reducible to pi, or we already have evidence that this is not possible? Okay, so let's start here. When will this be not possible? So when does a problem not reduce to, or how do you convince me that, okay, hey, look, there is this problem, this cannot be reduced to TSP? There is no way that this can be true. So do you know of any such problems which is, in some sense harder than TSP or something? So I heard you have learned about this problem in your TOC lectures. So those of you attend, of course, we will be talking about that problem anyway. Yeah, so the question I'm asking is the following, that I have set out with this ambitious goal of proving that all the computational problem in the world are reducible to TSP. Okay, so if you so if you are able to show that, then this will convince you that TSP is very hard. So the question I'm asking is, do you think this is an over ambitious goal, or is there a reason to believe that this is not possible? Right, good. So I have a few answers, and those are the correct answers. So there are indeed problems for which this is not possible. Okay, so one example is no, so not possible. Okay, so for example, in the case of halting problem, right? Problem, well, so the halting problem asks a question, asks the following question. It's again a decision problem. So given P and an input I, does P halt on instance I? So this is the key. I give you a program and I give an input to that program. Now, is there an algorithm? In some sense, is there a simulation which will tell you that, okay, not necessarily a simulation, but is there an algorithm that will look at the program and this input and tell you whether this program is ever going to terminate upon this input or not? Okay. So you have to give me another program which solves this problem, this yes, no answer. Now it turns out that this problem is essentially unsolvable. So in technical terms, we call these problems to be undecidable, but essentially it means that it cannot be solved by any reasonable algorithm. It cannot be solved. So forget about efficiency, running time, anything. So there are pathological examples for which any algorithm will actually not be able to, so any algorithm that runs for finite amount of time won't be able to give you a yes no answer. Okay, so this was proved by Turing. So this was proved by Alan Turing in 36, that HP is undecidable. Okay, which means that no algorithm running in finite time can solve this problem, can solve HP. Okay, so now so there is a problem like this, but why do we say that this problem is not reducible to TSP? Why are we so convinced about that fact? Well, the simple reason is because I know that TSP at least has a brute force algorithm. Okay, so it's true that we do not know an efficient algorithm to solve TSP, but at least we know there is a finite algorithm. You can, as we discussed last time, you can go over all possible permutation of vertices, and you can check which of these give you a cycle that visits every vertex exactly once, and you can check the length of this cycle. If it's less than k, then it's an yes. If it's no, then it's an, right? So at least TSP has a finite run, the brute force algorithm for TSP has a finite runtime. Okay, so now by contradiction, we can show that HP is not reducible to TSP, right? So suppose HP was reducible to TSP in polynomial time, but then you can clearly use this brute force algorithm to solve the halting problem as well. Yeah, but Turing proved that that is not possible. So which means that this super ambitious goal of proving all computational problems in the world are at most as hard as TSP, this is a very this is a, it's not a true conjecture. Okay, so we have to lower our expectations. So TSP is hard, but इतना भी hard नहीं है, ठीक है, उससे भी harder problems है. This is what this is showing. Okay, so let's now reduce the size of our set a little bit. Okay, so ठीक है, what, the place where we got stuck here is that TSP has a brute force solution. Okay, so let's actually turn this thing upon its head. So let's ask. So question 2 is, suppose now I give you the set of all problems that are solvable by brute force. Okay, it's not clear what this exactly means. We will make this notion a bit more formal, but in our mind, at least at an intuitive level, we know what this means. Okay, what this means essentially is that you pick all possible solutions to the problem and you try them one after the other. Okay, so let's look at that class of problem. This is clearly a subset of all the computational problems in the world, and the question is this true now? Okay, so again, think of pi as, let's say, 3SAT or TSP or whatever, any hard problem you want. Now, can we prove that all the problems that are solvable by brute force, they can be polynomially reduced to this problem? Okay, so in order to at least start formalizing this notion, I have to tell you what solving by brute force precisely means in a more formal way. So again, at an intuitive level, it just means that you pick any possible solution and you just check whether this is a valid solution or not. You throw away that solution. If it's not, then you pick another solution. Then you keep doing this. Okay. So now, again, let me ask you this question. What do you think is an essential characteristic of a problem from an algorithmic point of view, such that it will admit a brute force solution? What has to happen? I have already told you the answer, in fact, in the last sentence that I said. So what kind of an algorithm has to exist if you hope to solve some problem using brute force in this sense of the term? So think of any general problem, and let's say you want to solve it using brute force. So when can you do that? So the question is, right? Yeah, the answer, yeah, exponential. So you can take any amount of time. So I don't care about runtime here. Okay, so we are not in the domain of polynomial time anymore. So yeah, it could be exponential. But the question is that, the question I'm asking is, when can you hope that a decision problem will have a solution which is exponential? Yeah, decidable is a technical term. I'm asking a slightly simpler question. I'm asking the question that, okay, take the example of TSP. Okay, so what really allows you to solve TSP in exponential time? What is the characteristic of TSP? So that, great. I'm so glad. So both these two answers actually together answer my question. Okay, so one answer is if we can check all possible combinations, yeah, and the second answer is that there has to be finitely many combinations. Yes, if both of these things are valid, then I can use a brute force algorithm. Yeah, so it doesn't matter which problem I'm talking about. So this is a very general way of characterizing problems such that they will have a brute force solution. Okay, so solving by brute force. Okay, so number one, there has to be finitely many possible solutions. Okay, and the second thing is, we should be able to check if some candidate solution is correct or not. Okay. Okay. So I'm not talking about how much time I will take, but these two, I mean, so the first thing is that, there should be finitely many possibilities so that I can go over all of them one by one, and eventually this process will end. And the second thing is, for each of the solutions, I'm trying to verify whether this is a valid solution or not. So such an algorithm at least has to exist, right? So given a solution, I need to check whether it's a valid solution or not, and at least I need an algorithm that will perform this task for me. Yeah, and this has to also run in finite time. Okay. So this kind of algorithms have a special name. So they are called verifier algorithms. Okay. So what is a verifier algorithm? Given a decision problem and a possible solution to the problem, the verifier basically tests whether it's a valid solution or not. If it's a valid solution, it will say yes. If it's not a valid solution, it will say no. As simple as that. Okay. Great. So yeah, so that is all actually. Yeah, this is a definition of, I mean, not a definition, but this is what I mean. Yeah. Yes. So I was hoping that someone will ask this question. So what Atisha is asking is, yeah, so is there an example of a problem for which we can't verify a solution? Any undecidable problem falls in this category, but let me actually give you another example, which is almost similar to what we saw, but here you cannot verify. So this is known as counting. So example of problems with no, so let me say no fast verifier. Okay, so I'm doing a bit of a cheating here. So it's not true that the example that okay, Atisha, let's do it like this. So let me introduce formally what I want to do, then at the end I will give you this example. Okay, because the example which I was trying to show, this will probably have a finite time verifier, but we want something more out of our verifier. We are not so the thing that I'm going to define cannot, yeah, it does not admit, let's say, exponential time verifiers. Okay, so such examples I can give you, but let's just hold on for a moment. Okay, so this brings us to this classification of problems which we called NP. Okay, so the class NP. Right. So essentially, these are, problems. I mean, at least this is a class of problem which can be solved using brute force. There are other problems outside NP, outside the class NP, which can also be solved using brute force, but these are definitely solvable using brute force. But we want more out of these problems. Okay. So the semi-formal definition is the following. So semi-formal. Right. So problem 5 is in NP if there exists a polynomial time verifier for pi. Okay, so what is a polynomial time verifier? So polytime verifier is given pi and a candidate solution S of polynomial size, the verifier should return yes if S is a valid solution and a no if S is not valid. Okay, so again, this is semi-formal definition. I'm not precisely defining the class NP, but this is what the class NP means. So you pick a problem, yeah, and you just ask yourself this question, that if I'm presented with a solution to this problem, which is of polynomial size, then can you then does there exist an algorithm which in polynomial time will say whether this problem is whether this solution is a valid solution or not? So the question is, what do I mean by polynomial size? Yeah, the size of the solution is polynomial in n. The size of the solution that is presented to this verifier is a polynomial in the size of the input. This is what it means. Yeah, the size of the solution has to be also polynomial, right? Right. So this is like a stricter, this is somewhat a stricter requirement than what was said previously. So previously, Atisha says that, okay, as long as there are finitely many possibilities, this is okay. But now we are having a more strict requirement. We are saying that, you know, the purported solutions has to be written. I mean, we can write down these solutions using polynomially many number of bits in some sense. Yeah. So that's how the class NP is defined. Okay. So more or less, is it clear what NP means? That's correct. That's absolutely correct, Oshin. This does not include all brute force, all the problems that are solvable using brute force, because there might be some brute force algorithms for which the verifier is also not polynomial time, but the verifier itself takes exponential time. Okay, but those problems do not belong to the class NP. Okay, good. Okay, so what is NP? So let me just tell you. So NP means, okay, what is does not mean? So NP does not stand for non-polynomial. Okay, it does not stand for not possible. Okay, it does not stand for no problem. So who knows what does NP stand for? So what is NP an acronym for? Very good. So NP stands for non-deterministic polynomial time. Okay. So if this verifier exists, then we say that this problem is then this problem belongs to the class of non-deterministic polynomial time solvable problems. Okay. Now this is a completely impractical notion. Let me tell you straight away, because non-deterministic algorithms cannot be simulated. I mean, cannot be simulated using a sort of a real computer in life. But this is a very important idea for the theoretical study of computation. Okay, so again, if you take a course on TOC, then you will learn about non-deterministic automata and things like that. And the reason they are called non-deterministic polynomial time, so I again won't go into detail of why they're called like this, but essentially what you can do is, if this kind of verifier exists, then at a very, very high level, what you can do is you can check all the solutions very fast, and non-determinism somehow allows you, this is a very crude sense I'm saying, somehow non-determinism allow you to verify a lot of solutions in parallel, if you want to think about it like that. Okay, it's not at all correct what I'm saying, but just to give you a notion that if this verifier exists and you have a non-deterministic machine, then you will be able to solve these problems in real polynomial time. This is what this means. And as we said, this might not be the case for several other problems in the world, and we will see an example at the end. Okay, so is the definition of NP clear? So definition is just this: if there is a polynomial time verifier, that's it. Okay, and so I forgot to mention the class P. So P is the class of problems that you can actually solve in polynomial time, solvable in polynomial time. Okay, are there any questions about these definitions? Good. So now that we have defined this class of problem, so let's just do a quick sanity check of, we have defined a class, but does there exist any problem at all in the class NP? So by the way, what do you think is the relationship between the set P and the set NP? So these are two sets of problems. How are these sets relate to each other? We don't know. That's not true. We know something. We don't know the entire picture. Okay, less than. Very good. Yeah, so essentially this is the picture. So this is NP, but this is P. So this is we know. What we don't know is whether we can extend this to here. So this is the open question. Okay. So P is a strict subset of NP, and this is very clear, because if you can solve a problem in polynomial time, then it's totally clear that you can also verify a problem in polynomial time. Okay. Okay. Now let's see. Is TSP in NP? Well, clearly TSP is NP, because if you give me a permutation of vertices, that's your purported solution. And now you can easily design an algorithm which in linear time will check whether this is a valid solution or not. Okay? Is for example, independent set in an NP problem? Clearly it is, right? Given a subset of vertices, you can easily check whether it's an independent set and whether it has size k. Similarly, SAT is also in NP. So all these are problems which are in NP. Okay? So what is not in NP? So problem not in NP, not in NP. So one very extreme example would be halting. Okay. Another problem is counting independent sets. Okay. So the problem is same as IS, but the question is does there exist k independent sets in G? Okay, so now I am not interested in finding the size of the maximum independent set, but I am rather interested in counting the total number of independent sets in my graph. You just have to give me this answer, that how many independent sets exist. That's all. And let's say I give you some number k. So I'm taking the decision version of this problem. So I give you a number k, and I ask you the question that does there exist at least k independent sets in your graph? Okay, so this problem is not in NP. Yeah, so if you think about it, it's not at all clear how to design a verifier for this problem. Yeah, okay. So if I tell you that some bloke comes and tell you that, hey, look, this is this is a solution, it's not at all clear how to check whether, because then you have to check several possibilities essentially. That's right. But remember, the definition of NP means that the verifier has to run in polynomial time. If you check all possible subsets, then this is not polynomial time. Okay, this is very important. So if a problem has to be in NP, then the verifier has to run in polynomial time. Please keep this in mind. This is the only thing that you have to know about NP problems. Lakshya, does that answer your question? Good. Okay. So that brings us to the notion of NP hardness. Okay. So what is NP hard? So NP hard is a problem is, yes, Lakshya, that's correct. A problem is NP hard. So problem pi is NP hard if for all pi prime belonging to NP, pi prime is reducible to pi. Okay. So if all the problems that are in NP are reducible in polynomial time to problem pi, then we say that this problem pi is NP hard. Okay. Okay. Very simple definition. I mean, nothing much going on here. Finally, if pi belongs to NP and pi belongs to NP hard, then pi belongs to NP complete. Okay. Okay, so yeah, I'll pass this definition, but I have another question. Also in the definition, don't we have to consider that there are finite possible solutions for NP? Okay, so the point is, if the problem size is finite and each of your solution size is polynomial, then there could only be finitely many possibilities. Right? So which is why we require that S, the purported solutions S, these have to be, you have to be able to write this using polynomially many bits. So this along with the requirement that your problem itself has to be finite, those two essentially, you know, yeah. That's a good clarifying question. Okay. ठीक है. So अगर कोई problem NP hard है, in addition, if the problem itself is in NP, then we say that this problem is NP complete. Okay? So the point is that not every NP hard problem is itself NP. And we saw an example, right? So if you think about this counting independent set problem, then this problem is NP hard. So you can reduce any NP problem to this problem, but this itself is not an NP problem. Okay, so the picture somehow looks like that. So here is your set NP hard. Okay, and this is your set NP. Yeah, and then this is your set P. Okay, so there are problems which are not in NP. Okay, but if both these are satisfied, then we say that this is NP complete. Okay. Why is NP a subset of NP hard? Did I do this wrong? Oh, you are right. You are right. You are right. You are right. Sorry. This diagram is not correct. Yeah, you are right. Not necessarily. Yeah, it should be something like this. Absolutely. Yeah, very good. This is NP. Yeah. Yeah, sorry about that. Okay. So this intersection is what we call NPC. So this is NPC. Okay. Good. So now, we have done all these definition. Now, the final question that we have to sort of answer is, ठीक है, हमने define तो कर दिया ये NP complete class, but does there exist such problems at all? Yeah, I mean, can it happen that all NP problems in the world, they are incomparable? Yeah. So, or there is at least for each problem in NP, is it possible that there is at least another problem which is also in NP and neither of them is reducible to each other? Okay, can this happen? So that's the most remarkable theorem, I think, one of the most remarkable theorems in all of computer science, in fact. So Cook and Levin, somewhere in the 70s, proved that SAT is NPC. Okay. Yeah. Right. Okay. So Cook and Levin proved that this problem satisfiability, that is in fact an NP complete problem. So if you give me any NP problem, then I can show a polynomial time reduction from that problem to satisfiability. Okay. Of course, this proof is way beyond this course. It needs the ideas of Turing machine, and it will heavily use this concept of a polynomial time verifier and all that. But yeah, so one can prove such questions. Okay. Now this gives us a lot of power. Okay, so once this one theorem has been proved, now it opened the floodgate of proving that several other problems are in NPC. And why is that? Well, because now we can imagine, because I know that every problem in the world can be reduced, every NP problem can be reduced to SAT. Now this means that, let's say now you have a potentially new problem which is very hard. So maybe you are working on a project and you are stumbled with some problem and you think that this is NP hard. Then all you want to prove that this is NP complete. So all you need to prove is two things. First, you have to prove that this is in NP, yeah, which is typically very easy to do. You just have to produce a verifier. And secondly, you just have to show that some problem which has already been proved to be NP hard, that reduces to your new problem now. Okay, so what I'm saying is, for any problem, for any pi, if you can show pi belongs to NP and let's say SAT is reducible to pi, then pi belongs to NPC. Okay, so the seemingly daunting task of proving NP hardness, yeah, now because of Cook-Levin's theorem, now it has become relatively simpler. So all you have to do is you have to take your problem and show that some proven NP hard problem reduces to your problem. Please note, this is not the other way around. Okay, you cannot, it does not help to show that your problem reduces to an NP hard problem. That does not give you any new information, right? That's of course already true. But the other direction, if you can prove this, that will make a lot of sense. Okay, that will show that your problem is also NP complete, provided it itself is in NP. Yeah. For example, now we can safely say that IS is in NPC. Yeah, because I know that IS is itself NP and 3SAT reduces to IS and SAT reduces to 3SAT. We did not prove it formally, but yeah, you have to just accept it. Okay. तो ये है पूरी कहानी, पूरी नहीं मतलब this is like a very bird's eye view of hardness and stuff. Yeah, so it's all about reductions essentially. So of the very same flavor that we saw a couple of examples. So any questions about this? Okay, there were a couple of questions meanwhile, but seems to have been resolved. What would be an example of a problem in NP and not NP hard? Yeah. So P is an, yeah, I draw that completely wrong, that figure. Yeah, P is. So TSP is also NP complete. Yeah, vertex cover is NP complete. There are several others. Okay. But please keep in mind that there are problems which are harder than these problems. Okay. So, okay, so that officially is the end of the course. So in tomorrow's tute, I will actually ask the TS to do a few more reductions, right? Because yeah, so some other, I mean, we did not see too many reductions in this lecture. We just saw 2 of them. So hopefully in the tute you will see 3 or 4 more. I mean, they are fun to do. Yeah. So given one problem, you will have to kind of, again, given a yes instance, you show a yes instance to the other one, and so on and so forth. So that's it. So any questions? What is an example of NP hard and not NPC? Yeah, this counting independent set problem, right? That's NP hard, but it's not NPC because it itself is not an NP problem. Oh, great. So coloring of a graph in general is NP hard. So what is the coloring problem? So coloring. So the coloring problem asks the following question. So basically, let's say you are given a graph. Okay. And now you have to assign colors to your vertices such that 2 endpoints of an edge should not receive the same color. Okay, that's the coloring problem. So this is a valid coloring, for example. Right. Okay. So that's the valid coloring of your graph. Okay. Good. So now there is a notion of a chromatic number of a graph. So the chromatic number is the minimum number of color that you require to which is not valid. This is not valid. Okay. Okay. Good. Sorry. ठीक है, कुछ और कलर दे दीजिए इसको. Yeah, there's a triangle, so I need this one. Yeah. Okay. Yeah. So answering that question, yeah. So there's a notion of a chromatic number of a graph, which is the minimum number of colors that you require in order to produce a valid coloring of your vertices. Okay. And finding this chromatic number is NP hard. It's a very hard problem actually. Yeah. For some other reasons. Okay. But do you think this is an NP? This is a problem in NP? Isha, is this problem in NP? So if I ask you the following question, that given a graph, can you color this correctly with K colors? Is this problem in NP? So can you verify this in polynomial time? No. Why not? So remember, the solution here is right. Yeah, right. So the solution here is a given coloring, right? So again, you can do a brute force algorithm for this question, right? So essentially you can, okay, so the point is, how many colors will you require at the most? You can require n colors. Yeah. What is the chromatic number? Oh yeah, yeah. The chromatic number question is not, but this decision question. So if I give you a K and I ask, does there exist a valid coloring which uses only K colors? This is an NP problem, right? But if you can solve this question, then by doing binary search, you can also solve the chromatic number question, right? Right. Okay, there were some other questions. NP hard don't need a polynomial time verifier then. No, 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 no. NP hard does not need anything. Okay, yeah, this is a very important thing to understand. NP hard just means that any problem in NP is polynomial time reducible to this problem. That's the only thing you require. You don't have any other requirement for the for the problem to be NP hard. Right. And in addition, if they have this polynomial time verifier, then they will be NP complete. Yeah. Any other question? Okay. So then I think that's it. So thank you for you know, staying with me through the course. And I know it has been difficult. The last part of the course, I really could not cover the way I wanted it to be. It would have been much better in a classroom, but let's hope that, yeah, at least we were able to do something. Heavy project deadline on 30th. Okay, so no, that's okay. I mean, I can just extend the deadline. Yeah. Deadline extension is not an issue. But yeah, I mean, yeah, it would be nice if you go through the problem. So that's all I want. So what project deadline do you have on 30th? DBMS. Okay. Yeah. So I can extend this thing. That's fine. Okay, so there would be a tute tomorrow. Please join. You will see a few more reductions. And so let's stop here today.